This week, we'll be talking about periodic trends. First, we must look at the word trend. What is a trend? According to Merriam-Webster, a trend is a general direction in which something is changing. We can think of trends maybe in the fashion world. I remember a couple of years ago when Uggs were really popular. Design trends would be maybe things like chevron as a pattern was popular for a while. Another trend would be when your parents talk about the stock market. They could say that that stock market is trending up or trending down. When we're talking about periodic trends, though, what we mean are the ways that characteristics change on the periodic table. So here are a few that we will be looking at today: the ionization energy, the electron affinity, the electronegativity, and the atomic radius. In order to analyze those periodic trends, we also need to understand what an effective nuclear charge is. So a nuclear charge refers to the nucleus of the atom. The nucleus is where we have the protons and the neutrons. Recall that the protons have a positive charge, whereas the neutrons are neutral. Therefore, the overall nucleus will hold a positive charge based on the number of protons. So an effective nuclear charge is now defined as the average nuclear charge felt by a single electron in an atom. And that's a point that we're now going to need to consider a formula that will help us find the effective nuclear charge of each individual electron within that atom. So why is this important? Is that a higher effective nuclear charge will mean that the electrons are more tightly held by the nucleus and are therefore harder to remove. This picture to the right shows kind of those important things we've been discussing with the effective nuclear charge. So we can see that the nucleus is in the center and it's positively charged. And if we want to refer to the effective nuclear charge, we need to find an electron of interest. So which electron are we going to start at in order to determine this effective nuclear charge? We have one labeled here, right there, an electron of interest. And then we need to consider the electrons that are between that electron and those of the nucleus. And they're found someplace in this green kind of cloud. And those electrons are going to cancel out some of our nuclear charge in order to lower that effective nuclear charge. Many times when we're finding the effective nuclear charge, we're looking at that in reference to a valence electron. We talked about valence electrons last week, and we said that those were the electrons that are found in the outermost orbital of the atom. We will use the following formula to calculate effective nuclear charge. The effective Z equals Z minus S. In this case, Z stands for the nuclear attraction, which really we're going to use as the number of protons. S stands for the shielding electrons. So those are the electrons that are in an energy shell below the electron that we are looking at. They are the electrons that are standing between the nucleus and our electron of interest. So therefore, in order to find our effective nuclear charge, we will take the number of protons and subtract out those shielding electrons. In our first example, we will look at phosphorus, and specifically an electron that is on the n equals 3 level. Here is a Bohr model of the phosphorus atom. In the center, we have the nucleus, which here is represented by 15p+. So that's telling us that the nucleus has 15 protons, and each proton has a positive charge. So we have a total of 15 positive charges in that nucleus. Recall that the neutrons do not hold a charge. Around that nucleus, we also have 15 electrons. We know that we have 15 protons and 15 electrons because phosphorus has an atomic number of 15. Those electrons are placed based on their electron configuration. We can see that we have 2 electrons in the first energy level, so it's 1s2. In our second energy level, we have 8 electrons. 2 of those are in the s, 2s2, and 6 of them would be in the p orbitals, so 2p6. In our final energy level, we have only 5 electrons, so 5 valence electrons for phosphorus. And these 5 electrons would be found in the s and p orbitals. We'd have 2 electrons in the s orbitals for 3s2, and 3 electrons in the p orbitals for 3p3. In order to find our effective nuclear charge, we therefore then need to first designate an electron of interest. We will be considering one that is on the 3rd energy level, so we can include this one. And now we're going to use our formula. So that's Z effective equals Z minus S. And so for Z, that's our number of protons. That's our nuclear charge. So that is 15. And then we're going to subtract out those number of shielding electrons. So our shielding electrons are all the electrons that are between our electron of interest and the nucleus. So we need to find the electrons that cover these two sections. So that would be 2 in the first energy level and 8 in the second. So that's a total of 10. So we would do 15 minus 10, and that does give us a net positive charge of plus 5. In our next example, we will look at sulfur. Sulfur is right next to phosphorus on the periodic table, and it has an atomic number of 16. We'll be looking at an electron in the n equals 3 level as well. So here we do have a Bohr model of the sulfur atom. That means that we have its electrons drawn in orbitals around the nucleus. We know that the nucleus does contain 16 protons because of its atomic number is 16, and therefore we have 16 positive charges in that nucleus. Recall our formula for effective nuclear charge is to take the number of protons and then subtract from that the number of inner electrons or shielding electrons. So we already said that we know our atomic number is 16, and that corresponds to the number of protons, which corresponds to the first part of our equation, which again is Z minus S. So Z is our atomic number, our number of protons. So we'll take 16 minus the number of shielding electrons. And just like with phosphorus, we have electrons in both the first and second energy levels. We've got 2 electrons in the first energy level, and then we have a total of 8 in the second energy level. So we have 2 plus 8 makes a total then of 10. So we have 10 shielding electrons. So if we do that math, 16 minus 10, that gives us positive 6. So our nucleus is exerting a plus 6 charge on those outer electrons. So those outer electrons there, if we look at one in that 3rd energy level, like I've just drawn with green at the bottom, if we're looking specifically at that electron, it is not feeling the full plus 16 charge of the nucleus, as is indicated by its number of protons. Because it's got some electrons between it in those first 2 shells, therefore, that electron in the last energy level is only feeling a plus 6 effective nuclear charge. It's being shielded. Part of those electrons are blocking that nucleus's power, and the electrons in the 3rd energy level are only feeling a plus 6 effective charge. One more time, here's our equation for effective nuclear charge. It is that we take the charge of the nucleus minus the shielding electrons. In our previous example of sulfur, it was 16 for the protons minus 10 for the shielding electrons, equaling 6. So now we're going to look at how effective nuclear charge changes as we move across the periodic table. We just looked at phosphorus and sulfur. So phosphorus is atomic number 15, located here. I'll put it in red. And sulfur is atomic number 16, right next to it. I'll put it in blue. Now, I know this is kind of blurry, so we can't specifically see a lot of those symbols. What we're mainly looking at here is how those effective nuclear charges change as we move across the periodic table. So we're looking at big picture right now. And we saw that phosphorus had an effective nuclear charge of +5. Put that in red, was +5. And then sulfur had an effective nuclear charge of +6. So we can see that as we move across toward the right, that did increase. And that does follow what this trend is listed as above. That's it's saying as we move right across the periodic table that we should see an increase in our effective nuclear charge. So let's look at why that might be. So as we're moving across a row, again assuming that we're not moving up and down, but just within that row and moving across, and we're starting at the left and going to the right, our atomic number is going to increase. So we start with sodium there at 11, then magnesium 12, aluminum 13, nickel 14, phosphorus at 15, and sulfur at 16. So as we're moving across, we're increasing atomic numbers, but we're also adding protons and electrons, because remember that atomic number corresponds to the number of protons and the number of electrons. So as we add more protons, that means that our nucleus has a larger positive charge. It simply has more protons in it, more charges that can help hold in the electrons. We are adding more electrons, but as we're adding them, they are staying at the same energy level. So we would only increase the energy level if they went into an orbital that had a higher floor. If we're thinking in the electron hotel analogy, if we put an electron on a higher floor, that would be what we mean when we have the higher energy level. So all of these electrons are going to be going into the third floor, the ones that we're looking at with sodium, magnesium, aluminum, and so on. So those are on the third row of the periodic table, and they're going in the 3s orbitals, and they're going in the 3p orbitals. They're not going in the fourth or the fifth floor. Those are staying on their level. So because of that, as we add electrons, they're still staying on the same place. That we're not adding more electrons that are between the nucleus and our outer electrons. So as we add more protons, that effective nuclear charge is going to increase for those electrons of interest. On the other hand, if we were to move up or down the periodic table, I think we'll look at down first. It makes a bit more sense to me with that. So as we move down the periodic table, we are increasing our energy level. That's what our numbers on the left-hand side of the periodic table are telling us. They're telling us that if we move down to the fourth row, that we are now putting electrons in our fourth energy level, or the fifth, or the sixth, or the seventh. So as we move down the periodic table, those electrons are being placed into orbitals that are much farther away from the nucleus than our lithium or our hydrogen atoms. So as we move down the periodic table, those electrons are much further away from the nucleus, and therefore they're not really feeling that charge of the nucleus quite as much, because there are a lot of electrons between that outer energy level and the nucleus. So therefore, conversely, if we move up the periodic table, that effective nuclear charge would increase, because we do have less than the amount of electrons between that nucleus and that outer energy level. So therefore they're closer together. That nucleus can hold a much stronger force on their electrons. So we've just finished exploring effective nuclear charge, which we will look at in these next few periodic trends to see how that affects the atomic radius, ionization energy, electron affinity, and electronegativity. Atomic radius is the next periodic trend we'll be looking at. And when you hear the word radius, you probably think of something you learned in math class with a circle. So we measure the radius of a circle by looking at the distance from the center of the circle to any point on its circumference, and we call that its radius. For atoms, they also have a radius from the nucleus to the outside of the atom, but it's hard for us to measure that because of the changing electrons in the cloud of the atom. So instead what we do is we take two atoms of the same type, and measure the distance between the nuclei of those two atoms. Then we divide it in half, and we say that that is its atomic radius. So essentially that distance between two nuclei would really be 2 times an atomic radius. So we have to half that number to get our atomic radius. It's usually measured in picometers. So as we start to observe atomic radius as a periodic trend, we're going to look at first the halogen group. So the halogen group is our second to last group on the periodic table if we're looking at it from left to right, right there next to our noble gases. So our first halogen is fluorine, here pictured on the left. And then the rest of our halogens, we would have to move down the periodic table directly below that to find chlorine, then bromine, then iodine. And as we can see from this graphic illustration, the atomic radius gets bigger as we move down the periodic table. So for fluorine, it's 64 picometers, chlorine, 99 picometers, bromine, 114 picometers, and iodine, 133 picometers. So as far as why that is, each time that we're moving down a row of the periodic table, we're adding another energy level to our atom. So fluorine's going to end in 2p5, chlorine would end in 3p5, bromine's electron configuration is going to end in 4p5, and iodine's electron configuration will end in 5p5. So each of those additional energy levels means that those electrons are much further away from the nucleus and are not held nearly as tightly by the nucleus, therefore resulting in a larger atomic radius. The 4 atoms we just observed on the previous page are right here, and we can see that those move down the periodic table and are getting slightly larger as we move down the periodic table. The other trend for atomic radius is that atomic radius actually decreases as we move to the right across the periodic table. So we just observed that atomic radius is going to increase as we move down the periodic table, and we know that that's because we're adding more electrons that are going into higher energy levels that are farther away from the nucleus. But as we move across the periodic table to the right, we can see that that atomic radius is getting much smaller. And that's because as we move right across the periodic table, we have more protons in the nucleus. And as we have more protons, we have a higher effective nuclear charge. And that higher effective nuclear charge is going to create basically a stronger pulling nucleus that is able to pull in those electrons a little bit more tightly, causing a smaller atomic radius. So our atomic radius periodic trend is that it decreases as we move to the right across the periodic table row, and it increases as we move down the column. Generally, when we're referring to an atomic radius, we mean the neutral version of an atom. If we are talking instead about a charged version of an atom, we mean a cation or an anion. So a cation or an anion is an ionized version of an atom. You've heard the word ionized before when we looked at plasma at the beginning of the matter unit. We talked about how plasma was an ionized gas, and that meant that rather than a gas which has neutral particles, the ionized plasma had positive and negative gas particles, and that would create electrical currents. So cations and anions are similar to that in that they're ionized, meaning they either have a positive or a negative charge. So this picture to the right helps explain the difference between a cation and an anion, and in relation to them either wanting to gain or add an electron, which causes them to change charges. So sodium is characteristic of an element that's on the left side of the periodic table, which has a tendency to lose electrons. Sodium's electron configuration ends with it having just one electron in its s orbital, and it would rather get rid of that electron in order to get a full valence shell. It does not want to add more electrons. Instead, elements on the right-hand side of the periodic table, like chlorine, would prefer to add an extra electron. Chlorine specifically has 7 electrons in its valence shell, so we know that it would like to add one more electron in order to have a full valence shell. So that's what's going on in this picture. Sodium's saying, no, just take it, please. And chlorine's like, oh yeah, don't mind if I do. It would love that electron. Let's take a closer look at how a cation is formed. So a cation is a positively charged version of an atom, and this happens when an atom loses an electron. So on this left-hand side, we've got an atom here that has 3 protons in the nucleus in the center, the positive charges, and 3 electrons around that orbiting the nucleus. So if that atom were to lose an electron, it now has 2 electrons, but still 3 protons. So therefore, overall, it now has a positive 1 charge because we've got +3 for the positive and -2 for the negative. So 3 minus 2 would be +1. So it's now a positively charged atom. So if this is a little confusing to think of, another analogy would be kind of considering maybe a car loan. So a car loan is a liability, it's a debt, and therefore if you were to get rid of your debt, pay off your car loan, you would effectively have a higher net worth and you would have kind of be like having positive more money. So that's similar to this. If we lose something negative, we become more positive. And that's how a cation forms. An anion is pretty much the opposite. An anion is when we become more negative. So if we start with the same atom that has 3 protons in the center and 3 electrons around that, now we're going to add an extra electron. So that anion gets an electron and now it is negatively charged. And we can see that because there's 4 negative charges, so -4, and then we'd add 3 positive charges. So therefore we'd still have a -1 charge. So an anion is when we become more negative by adding an electron. When we form a cation or an anion, it changes the size of the atom. We call this its ionic radius. So an ionic radius can either be larger or smaller than the atom, depending on if we either added or lost electrons. So a cation, again, is the one that becomes positive as we lose electrons. So our examples here are going to be lithium in blue, beryllium in red, sodium in green, and magnesium in gold. So those are our cations that I've just put a box around there. All right, cations at the top. So cations are going to lose 1, or in this case we have magnesium and beryllium losing 2 electrons. And as we can see here, those ionized versions of the atom are going to become much smaller. In the case of lithium, it's becoming like almost a quarter of its original size. So because it has less electrons, it now has a net positive charge, and that nucleus can pull in those outer electrons a little bit more tightly. So that becomes a much smaller atom instead. On the other hand, an anion generally becomes bigger. So our examples of anions over here are fluorine and chlorine, both of which are halogens. So fluorine and chlorine are instead going to gain electrons. And when they gain electrons, they're going to have a net negative charge. And the nucleus is not going to be able to hold those electrons in as tightly. So they're going to become much larger. So we can see that here, and they almost actually over double the size of both chlorine and fluorine when they become anions. All right, so now that we've looked at cations and anions, we now want to look at the energy required to create those. So a cation, again, is when we remove an electron from an atom in order for it to become positively charged. That costs energy. So in order to do that, we put energy into the atom in what's called an ionization energy. We express this in kilojoules per mole. Mole is a unit of measure telling us a certain number of particles, 6.02 times 10 to the 23rd. So a very large number of molecules. So but the one thing to notice on this chart here is that the amount of energy required to take off the first electron versus the second or third or even fourth electron could be very different. So we've got an aluminum atom that we're starting off with here, and if we want to remove one of its electrons and make it positively charged, it would require 580 kilojoules per mole of energy we'd have to put into the atom, and then the electron could be taken off. But if we want to take off a second electron, we're going to have to pay another 1,815 kilojoules per mole of energy. A third one's going to cost 2,740 kilojoules per mole of energy, And finally, if we're trying to take off a fourth electron from aluminum, it's going to cost 11,600 kilojoules per mole of energy. So it's a lot of energy to take off that specific electron. Ionization energy is going to follow a similar trend to the effective nuclear charge trend that we looked at the beginning of this lesson. So that means that it's going to increase as we move up the periodic table and increase as we move to the right across the periodic table. And we can think about that with a couple examples. So we'll look at francium in the bottom left-hand corner first. And so francium's electron configuration is going to end in 7s1. The reason we can see that from the periodic table is that it's in the 7th row. If we count down, and then it's in the S block, and it's in the first row of that. So we can know just based on the periodic table that its electron configuration would end in 7s1. That means it has one valence electron in that final shell, and it's in the 7th energy level. It's quite far from the nucleus. So therefore, it's not going to take us much energy to remove that electron because it really doesn't want that electron in the first place. It would be more stable without it. And that electron is very far away from the nucleus. On the other side of the periodic table, if we go all the way to the up and all the way over, we can look at fluorine. So fluorine's electron configuration is going to end in 2p5. That means that it has a total of 7 electrons in its valence shell, and that's because on the other side of the periodic table we had our 2s2, so we have to add the 2s and the 2p together to make our valence. So that's a total of 7 then. So it's got 7 electrons and it wants to get to 8. So giving up an electron for fluorine isn't going to get it any closer, so it really does not want to give up that electron. And that electron is really close to the nucleus. It's only in the 2nd energy level. So if we need to take off an electron from fluorine, it's going to cost a lot of energy because it really does not want to give up that electron. So again, our ionization energy is going to increase as we move up the periodic table because those electrons are much closer to the nucleus and held on much more tightly. And it's going to increase as we move right across the periodic table because it has more electrons in each shell as we move further to the right, and therefore it's closer and closer to 8, and it would rather gain electrons than give any up. Sometimes it's helpful to look at these trends in a 3D chart. So here's one for ionization energy. So same chart we just looked at as far as the trend itself, but just a different kind of way to show that. And on this one, it's more easily able to see a stark difference between ionization energies for our S block and our P block. So the further we get to the right, specifically near the top of the periodic table, we can see those ionization energies are so much higher than our ionization energies down here at this section of the periodic table. So we just looked at ionization energy, which is the energy required to take off an electron. However, now we're going to reverse that and we're going to look at the energy that is released when we receive an electron. So that's what's called an electron affinity. So electron affinity is defined as the amount of energy that is released when an electron is absorbed by a neutral atom to form a negative ion, aka an anion. So we've got an example down here at the bottom of chlorine. So if we've got chlorine, a neutral atom of it, and now we want to add an electron to it, now it becomes a negative atom, which is called an anion. And in that situation, we also have a release of energy. So negative 349 kilojoules per mole of energy is released. That's what that delta E means. Delta means change, and E stands for energy. So the change in energy is negative 349 kilojoules per mole. And it's written as a negative because negative indicates that the atom lost it. So that energy is being released by the atom going out into the surroundings. Surprise, surprise, electron affinity follows the identical trend we just looked at as well, same as our effective nuclear charge trend from the beginning, which is that it increases as we move up the periodic table and as we move to the right across a periodic table. So if we look at the same two elements we were looking at previously, francium would have a very low electron affinity. It's not going to be much more stable if we add a second electron to its 7th energy level. So it's not going to release much energy because it's not much more stable. On the other hand, if fluorine were to gain another electron, it would be in a much more stable energy level, and therefore it would release a lot of energy as well. So this is going to follow that same trend. As we move up the periodic table, it's going to increase, and as we move to the right across the periodic table, it will increase. There are some notable exceptions to electron affinity, and this 3D version of the electron affinity periodic trend helps show that, specifically in regards to the noble gases. The noble gases aren't going to be more stable if we add on another electron, so those don't have any electron affinity even shown here on this trend. But otherwise it does generally follow where it's going to increase as we move up and as we move across to the right. The last periodic trend we're going to look at today is electronegativity. So this is a little bit different from the last two that we looked at in that we're no longer measuring energy. Instead, this is a measure of how strongly atoms attract electrons to themselves. And when I say a measure, it's really more kind of an arbitrary number that is assigned to it in what's called the Pauling scale. This Pauling scale goes from 0 to 4, and fluorine has the highest electronegativity at 3.98. So this picture to the right kind of shows it here. We've got an atom, they've named atom, and it's how strongly that atom is going to work to attract electrons to itself. So some atoms, as we've just seen, really would like to add another electron as they'll get a lot closer to a full valence shell, whereas other atoms don't really care about adding more electrons. They in fact would rather probably get rid of them. So electronegativity is that measure, is how strongly is that atom going to fight to get more electrons. Just like our last two trends though, this does follow the effective nuclear charge trend as well. So it's going to increase as we move up the periodic table and as we move right across the periodic table. And we can see this kind of as a measure again of how strongly those electrons are going to be attracted to that specific atom. So if we start with our favorite one down here, francium, its electron configuration again is 7s1. So its last electron is in the 7th energy level, and there's just one of them in that energy level. So it doesn't really want to get more electrons. It's not getting much closer to a valence shell, a full valence shell by adding electrons. It would rather give one up. So it's not going to have a very strong electronegativity number. On the other hand, fluorine is our most electronegative atom over here at the far right and top side of the periodic table, and it's got 7 electrons in its valence shell. So it really wants to add another electron to be full. It also has its electrons in the 2nd energy level, which are very close to the nucleus. And therefore we know based on our effective nuclear charge trend that the nucleus has a very strong pull on those electrons, and therefore it's a higher ability to attract other electrons to it. And here's the 3D version of a periodic table showing electronegativity with those numbers written down on them so we can more easily see which elements are really going to work hard to get extra electrons. So we know fluorine, but we can also see from this that oxygen, nitrogen, carbon, phosphorus, sulfur, chlorine, selenium, bromine, iodine, those all have pretty high electronegativity numbers as well. So they're going to want to attract electrons too. Our last two periodic trends sounded kind of similar to each other, so we're going to review a little bit of the differences. So electronegativity is really a property that determines the tendency of an atom to attract electrons to itself. Whereas on the other hand, electron affinity is the amount of energy that is released when an electron is added to a neutral atom. So that is a measurement of energy that can be experimentally observed and calculated. For our final slide, I wanted to review cations and anions with this cute picture of a cat, because it'll help you remember the difference between a cation and an anion. So here we have a cation, which is an ion with a positive charge. That's a pun because cats have paws. Also, the cutest ion ever. It's not a super easy way to remember an anion. So if you remember, a cation is positively charged because it lost electrons. It's lost its negative charge. Then remember that the opposite of that is an anion, which is negatively charged because it has more electrons. It has more negative charges. So that's where I'll leave you.